Hello, today we're going to be looking at probability. It's a little chewy, this stuff, so bear with me. So probability is the likelihood that a given event or something will occur. We deal with it when we deal with games, a lot of probability in games. Also deal with probability in weather when they give you what % chance it is that it's going to rain on Tuesday or whatever. So ways of determining probability, there's empirical, there's basically seeing how often something occurs. There's theoretical, which is using how many times something should happen versus how many times it does happen. That didn't really come out that right, but just bear with me. But basically the theoretical is what we're going to be doing today. And then there's subjective. Sometimes engineers have to basically guess at something, what % chance they think something is going to fail within a 10-year period, just because there's no data for it. So probability components, there's an experiment. This is a test that you do, or an activity with observable results. There's a sample space. This is all the different things that can happen. There's the event. This is one of those possible outcomes. And then there's the actual outcome or sample point. This is actually what happens as a result of your experiment. What is the probability of a tossed coin landing heads up? So we flip a coin. What we can do is set up a probability tree, which basically branches off for each possibility. So if I flip a coin, it can either land heads or it can land tails. So there's the event is that we think that we want to know the probability that it will land on on heads. That'll be the event. And then there's the outcome, and it actually lands on heads. So there's just a sample there. Probability is a way of communicating the belief that an event will occur. Probability is usually expressed as a number between 0 and 1, or it can be expressed as a fraction, %, decimal as is indicated by 0 to 1, or by odds. The total probability of all possible events should total 1 if you're dealing with decimals. Okay, relative frequency. Fx is your relative frequency of x. Okay, n is the number of events that happen with outcome x. Okay, and n is the total number of events that occur, so the total number of possibilities. Okay, so this is usually expressed as a number between 0 and 1. The total possibility should end up being 1. So what is the probability of a tossed coin landing heads up? Well, how many desirable outcomes are possible? Well, that's 1. We want it to land heads up. Okay, so that's the one. How many total possible outcomes are possible? That's 2. So our relative frequency is there's 1 possibility that we're interested in that's landing heads. F is the total number of possibles. That's 2. So it's 1/2. So the probability of landing on heads is 1/2. We didn't really need or 50%. We didn't really need a lot of fancy work to tell us that, but this is just kind of going through the basic mechanics of the process. Okay. What was the probability of the coin landing tails up? Well, okay, that's the other possibility, and it has to add up to 1, so it's 0.5 as well. Okay. What is the probability of tossing a coin and having it land on heads both times? Okay. How many desirable outcomes are there, and how many possible outcomes are there? So here we went ahead and fleshed out our probability tree. So this is the first flip, it lands on heads, and then after that it's got another possibility of landing on heads or tails. So on this branch it landed on heads and then heads again. On this branch it landed on heads the first time and then landed on tails the second time. Okay, and on this one it landed on tails the first flip, okay, and then on this branch it landed on heads the second flip, and so on. Okay, so heads and heads, heads, tails, tails, heads, and then tails, tails. Okay, How many desirable outcomes are there? Well, there's only one outcome where it lands on heads both times, and that's this guy right here. How many total outcomes are possible? Well, there's 4 total possible. All 4 of these, 1, 2, 3, 4. So our relative frequency or our probability is 1 out of 4, or 20.25 or 25%. Okay. What is the probability of tossing a coin 3 times and having it land on head exactly 2 times? Okay, so we'll set up our probability tree again. So first we can land on, oh, they got fancy and use actual tails and heads. Heads then tails. So that's the first flip. This is the second flip. Okay, and here's the third flip. Okay, and then they do the work for you here. Okay, so how many of these did it land on heads exactly 2 times? The first one, no, it didn't. It landed on heads 3 times. This guy landed on heads twice. This guy landed on heads twice. Not here. Here it did. Not here, not here, not here. So 3. Okay, so there's 3 desirable outcomes, or the number that goes on top. And how many outcomes total are possible? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 total possible. So our probability is equal to 3 over 8, or 0.375, or 37.5%. Okay. The binomial process. So in using the binomial process, each trial has only 2 possible outcomes, like heads or tails, yes or no, on and off, right or wrong. Okay. So one thing to keep in mind is one coin flip does not influence the probability of the second flip or the third flip or the fourth flip. So if you toss a coin and it lands on heads 49 times in a row, okay, that 50th time to flip a coin, you still have a 50% chance of landing on heads again. It doesn't somehow diminish based on past tosses. Okay, so this equation looks a little chewy. It's not quite as bad as it seems. So this is a way of calculating the probability of something that only has 2 outcomes for each trial. Okay, so N here is, well, P is the probability. Okay, that's the result of our calculation. X is the number of times an outcome will occur within N trials. So basically, how many times are you going to land on heads? Okay, that's X. So you see X 1, 2, 3, 4 times. You might be wondering about this exclamation mark. That's a factorial symbol. You may have seen it before. Maybe you didn't. What that means is if you see 3 factorial means 3 times 2 times 1. 4 factorial means 4 times 3 times 2 times 1, etc. So you just multiply on down to 1. All right. Anyway, so N is the number of trials you're going to see, so how many times are you going to flip the coin? P is the probability of success on a single trial. So as we just looked at before, flipping a coin and landing on heads, if that's a success, you've got a 50% or 0.5, and that's what you would plug in as 0.5. And Q is the probability of failure. Well, that would also be 0.5 as well for a binomial process. So they'll all be 2. This I found. I don't know how exactly I found this, but I was browsing through something, and this. I'm not going to read this whole thing to you, but this is using the binomial process to figure out what are the chances of encountering a shiny scyther with 30 tries. If you've got a 1 in 450 chance on each try of getting a shiny. So anyway, as I say, nerds unite. I still play Pokemon Go, although I'm starting to drift away from it. Starting to lose its draw. Okay, so what is the probability of tossing a coin 3 times and having it land heads up 2 times? Okay, so we're going to use the binomial process. Okay, so So we're flipping it 3 times, so that's n. So n factorial is 3 times 2 times 1. Okay. P is the probability of success, which landing on a given trial. So flipping a coin and having it land on head once, okay, you have a success possibility of 0.5. Okay. X is the number of successful outcomes, which we wanted to land on head exactly 2 times, so that's 2. Okay. Q is the likelihood of failure, which is, again, the same as likelihood of success, which is 50-50 or 0.5. Okay. And minus X is 1. Okay. And then X factorial is 2 times 1. And n minus X factorial is 1 factorial, which is 1 times 1. So, and you get the same result without having to do that whole probability tree and all that. This is just a little bit more compact. So if you were doing something with many trials and that sort of thing, that probability tree would get pretty bulky. So dealing with large numbers of trials. So if you flip a coin 5 times and you want to know, and we know that it should land on heads 50% of the time, but it's probably realistically not going to do that because just because it's probable doesn't mean it's going to happen. But what you find out is that the more times that you conduct this experiment and keep track of your results, the closer and closer it's going to get to that theoretical probability. So if you flip that coin 500 times and you want to know how many times it's going to land on heads, you calculate the relative frequency of that, it's going to be pretty close to 50%. So anyway, probability and, okay, which is multiplication. So these are independent events occurring simultaneously. And what you get is it's just the product of the individual probabilities. So if the events A and B are independent, which means one doesn't influence the result of another, then the probability of both A and B occurring is just the probability of A occurring times the probability of B occurring as well. Okay. So what is the probability of rolling a 4 on a single dice? Okay, well, there's 6 sides, so it's 1/6. Okay, so the probability of rolling a 4 is 1 out of 6. What's the probability of rolling a 1 on a single dice? Well, it's going to be the same as rolling a 4. Okay, it's 1/6. Okay, so what's the probability of rolling a 4 and then a 1 using 2 dice? Okay. Well, we just learned that if we want to calculate the probability of and, that means multiply the probability of the 2. So it's 1/6 times 1/6, okay, which is 2.78%. Okay. Or probability. Okay, this means addition. These are independent, just like the previous thing we were looking at, where rolling the 4 didn't have any effect on the outcome of rolling the second dice. So the rolling the 4 doesn't affect how likely it is to roll a 1. Okay. So independent events, again, such as the event A or event B, and basically it's just you add them up. So the probability of A or B happening, okay, is the probability of A plus the probability of B. Okay. So what's the probability of rolling 4 on a single dice? 1 out of 6. What's the probability of rolling 1 on a single dice? 1 out of 6. What's the probability of rolling a 4 or a 1 on a single die? Okay. Well, that is going to be, since it's or, we're going to add them. So it's 1/6 plus 1/6. That gives me 1/3 or 33%. Okay. So, and that should make sense with what you know about probabilities, from basic, just kind of going through life and that kind of thing. So, okay, the probability of something not occurring. Okay, this is kind of silly a little bit, but basically it's 1 minus the probability of whatever it is you're interested in. So what's the probability of A not occurring? Okay, it's 1 minus the probability of A. So what's the probability of not rolling a 1 on a single dice? Okay, so the probability of 1 minus the probability of rolling a 1. Okay, the probability of rolling a 1 is 1/6. Okay, so it's 5/6 or 83%. Okay, the probability of dependent events. So these you got to be kind of mindful of. What is the probability that the first card is an ace and the second card is a face card or a 10? Okay, so the first card is an ace and the second card is a face card or a 10. So a little bit of a review if you're not much of a gambler. How many cards are in a deck? 52. How many aces on our deck? Well, there's 4 suits, so there's 4 aces. And how many face cards are in the deck? Well, there's ace, king, queen for each suit, and there's 4 suits, so there's 12. Okay. How many 10s are in a deck? Okay, well, there'd be 4 of those as well, 1 for each suit. So a little bit of review for those of you non-gamblers. Okay. What is the probability that the first card is an ace? Okay, well, there's 4 aces in a deck, and there's 52 cards total. So the possibility that the first card you draw is an ace is 1/13, or 7.7%. Okay. Now let's say the first card was not a face card, so we know we still have 12 face cards left. What is the probability that the second card is a face card? Well, we still have 12 face cards left, but we're short 1 card because we drew 1 card out. So instead of 52, we've got 51. So that's 4/17, or roughly, or pretty closely, 23.5%. Okay, since the first card was not a 10, what's the probability that the second card was a 10? Okay, since there's only 4 10s in a deck, okay, and just as before, we've only got 51. This didn't happen. Okay, we're doing this instead. Okay, so there's 51 cards left, and so it's 4 divided by 51, and that gives us 7.8%. All right, 2 cards are dealt from a shuffle deck. What is the probability that the first card is an ace and the second card is a face or a 10? So we've got an and going on and we've got an or going on. So that means we're going to multiply something and we're going to add something. Okay. So how this is going to work out is, what is the probability that the first card is an ace, and that means multiply. So we're going to multiply, and means multiply. And the second card is a face, so probability of face, plus, okay, that means add, or means add, okay, plus the probability of a 10. Okay, so we just use these probabilities that we just calculated on the previous slide. So kind of a complicated process here, but hopefully it's making enough sense to you. Okay, so they're doing math, and the resulting percentage is 2.4%, or 0.0241. Okay, conditional probability. We've already gone over that. So this is Bayes' theorem. This looks pretty nasty. It's not quite as bad, at least not the problems that you're going to see with Project Lead the Way. If you just kind of take a little bit of a common sense approach to it, I'm going to show you an example, and we're going to look at it as basically the probability of A happening is basically how many units of A do we have over how many total units of the whole system do we have. Okay, the probability of A given E. So, all right, this is the problem. An LCD screen components for a large cell phone manufacturing company are outsourced to 3 different vendors. Vendors A, B, and C supply 60, 30, and 10% of the required LCD screen components. Quality control experts have determined that 0.7% of vendor A, 1.4% of vendor B, and 1.9% of vendor C components are defective. Okay, so we've got vendor A supplies the most product, but has the least number of defects, and vendor C supplies the least product and has the highest currency currency, not the word I'm looking for, rate of defects. Okay, so if a cell phone was chosen at random and the LCD screen was determined to be defective, what is the probability that the LCD screen was produced by vendor A? So basically what we want to do is look at how many defects does vendor A produce and divide that by the total number of defects that are being produced. And that's what we do. First off, I took the data that they gave us and I put it in a table because I think it makes a lot more sense in a table. So for vendor A, B, and C, here's their percent defective rate, okay, and here's the percent that they supply. So since we're looking at the probability that the defect came from vendor A, on top I put the percent defective times the percent supply. And that kind of gives us, in a roundabout way, basically how many defects they supply. Okay, and then we're going to divide that by the number of defects from A plus the number of defects from B and the number of defects from C. Okay, and when we calculate that out, we get 0.0478, or basically 41% chance that it came from vendor A. Okay, so Project Lead the Way works this out as well. It's a little bit more complicated. I'm going to flip through their slides just so you have them. So list the knowns, the probability of A, B, and C of seeing those. Number one, list the knowns, probability D, given A, D given B, D given C. They convert all these into probabilities as decimals. Okay. And then they basically come up with the same overall approach and get the same answer. So I think my approach makes a little bit more sense. So that is it for probability. Hopefully you're not drooling on your desk. I know that was kind of a chewy topic, but that's probably one of the harder things that we're going to go through through the end of the year. So anyway, good luck, have a good rest of your day, and work on the worksheet when I assign it.